Welcome back for another deep dive. This time, we're going to be talking about quantum mechanics.
Oh, fun!
But we're not going to be teaching quantum mechanics or anything.
Right.
We're really going to be looking at one of the most interesting figures from the field,
Yeah.
Erwin Schrödinger.
This is a great
Now,
way.
he wasn't just a brilliant physicist. I mean,
Right. He was so much more than that. He was a poet, he was a philosopher,
Huh.
really kind of a Renaissance man, and his life had some interesting turns. Like, did you know he almost became a linoleum salesman?
A linoleum salesman. Okay, you've got to tell me about that.
Oh, yeah.
So to do this deep dive, we're looking at excerpts from a Spanish language biography of Schrödinger. And it really covers everything. I mean, we're talking his personal life, his career path, and obviously his incredible work in quantum mechanics. I guess, what are we trying to do today? Like, what's our mission, I think, to get a sense of this guy, right? Like, who was he? And also try to understand these mind-bending paradoxes that came out of his work.
Yeah, I think that's a great way to put it. I mean, you really can't separate the man from the science, you know? And to understand his impact, we kind of have to understand him.
Yeah.
So he was born in Vienna back in 1887.
Okay.
And this was a really interesting time. I mean, Vienna at the turn of the century, I mean, this was, the birthplace of psychoanalysis, Art Nouveau, atonal music.
Wow.
So many revolutionary ideas swirling around. And this is the world that shaped Schrödinger's thinking.
I mean, so he's surrounded by, revolutionary ideas from when he's a kid?
Yeah.
I guess it makes sense he went on to kind of shake up the way we understand the universe.
Yeah, for sure.
And you mentioned he wasn't just into physics.
Right. Oh, absolutely. I mean, he was exposed to science pretty early. His grandfather was a chemist.
Okay.
But his interest went way beyond that, literature, poetry, philosophy. He was a true polymath.
Right.
I mean, he excelled at so many things. Stefan Zweig, who was like a famous Austrian writer, once said that if Schrödinger hadn't been such a brilliant physicist, he would have been like a celebrated poet.
That's amazing. I guess some people are just good at everything.
It seems like it.
But, okay, let's get back to the physics. I know a huge influence on Schrödinger was Ludwig Boltzmann, who was a pioneer in statistical mechanics. But Boltzmann, I mean, he didn't have it easy, right?
No, he didn't. I mean, his work was really controversial back then. And sadly, he actually ended up taking his own life, which I think really highlights the pressure that scientists can face when their ideas challenge the established way of thinking.
Oh, wow.
It's kind of a reminder of the human cost of scientific progress.
Yeah, absolutely. I mean, it takes a lot of courage to go against, what everyone else thinks.
Wow.
So how did Boltzmann's ideas shape Schrödinger's path?
Well, Schrödinger's early career, it was less about, making big pronouncements and more about refining existing work. Like getting the details right, ensuring accuracy in the framework that already existed. And it was really this attention to detail, this rigorous approach that kind of laid the foundation for his later breakthroughs.
Huh. So he went from refining things to completely revolutionizing the way we understand the atom.
Yeah.
That's quite the journey. But you mentioned earlier that there were some bumps along the way, right? Like financial struggles and this whole linoleum thing.
Yeah.
What happened there?
So after World War I, Vienna was in a really bad place economically.
Okay.
And Schrödinger, like a lot of people, was struggling to make ends meet. And at one point, he was so desperate for a stable income that he actually considered working in his father-in-law's linoleum factory.
Seriously.
Yeah.
The Schrödinger equation almost lost to the world of linoleum.
It's wild.
It's incredible how, different things could be. And it makes you think. So to really get his breakthrough, I think we need to understand the scientific landscape at the time.
Right. Exactly.
What was going on in physics back then?
Oh, imagine a world where the very foundations of physics are crumbling. I mean, classical physics, which had worked for centuries, was suddenly failing to explain some fundamental observations at the atomic level.
Wow.
It was a time of just incredible confusion and intellectual upheaval.
Yeah.
Even for the most brilliant minds, the physicist Wolfgang Pauli, he said, physics is very muddled again at the moment. It is much too hard for me anyway, and I wish I were a movie comedian or something of the sort and had never heard anything about physics.
It sounds like physics was in a real crisis, like it needed a new direction, a new way of thinking. What was Schrödinger's approach to all this?
Well, Schrödinger was really puzzled, like many physicists, by this strange and kind of counterintuitive behavior of atoms. And he really wasn't convinced by the approach that Heisenberg and his colleagues were taking in Göttingen, this abstract, matrix-based approach to quantum mechanics. He was looking for something more intuitive, something more visual, something that resonated with his background in classical physics.
So he was looking for like a different path, a different way to understand the quantum world. But I think before we jump into that, it might be helpful to rewind a bit and remind ourselves about some of the key discoveries that kind of set the stage for Schrödinger's breakthrough.
Sure, yeah.
I mean, what were some of those?
Well, I think it all started with this seemingly simple problem of trying to understand the light that's emitted by hot objects,
Hmm.
classical physics. It predicted that the intensity of that light would increase infinitely as the temperature went up.
Okay.
But experiments were showing something very different, like the actual spectrum of light that was emitted had a specific shape with a peak at a certain wavelength. And this discrepancy, which became known as the black body radiation problem, was really stumping physicists for years.
So classical physics, which had worked so well for so long, was hitting a wall when it came to these tiny particles.
Exactly.
How did they overcome that obstacle?
Well, it was Max Planck, a German physicist, who came up with this radical solution. He proposed that energy, instead of being continuous, could only be emitted or absorbed in these discrete packets or like quantum. It was like saying that energy came in these tiny little bundles, not this smooth, continuous flow.
So instead of a dimmer switch, where you can gradually adjust the light, it's more like flicking a light switch on or off with no in between.
That's a great analogy.
Okay.
And this concept, which became known as quantization, was a major departure from classical physics.
Yeah.
But it worked.
Oh.
Planck's formula perfectly explained what was being observed with the black body radiation.
Wow. So this idea of quantization was a total game changer.
It was.
Did other physicists pick up on it?
Oh, yeah, absolutely. In fact, in 1905, Einstein used this idea of quantized energy to explain another puzzling phenomenon, the photoelectric effect. And this effect, where light shining on a metal surface could eject electrons, it couldn't be explained by the classical wave theory of light.
Right.
So Einstein proposed that light itself was quantized, made up of these tiny little packets of energy called photons. It's like saying that light, which we think of as a wave, could also act like a particle.
That must have been mind-blowing back then. Light being both a wave and a particle. That's like challenges everything we think we know about how the world works.
It really does. It opened up this whole new way of thinking about light and matter. And a few years later, a French physicist, Louis de Broglie, took this idea even further. He wondered, if light, which we normally think of as a wave, can also behave like a particle, could it be that particles like electrons, which we normally think of as these little tiny balls of matter, could also behave like waves?
That's a pretty bold question. It's like he's saying, well, if you can do it, I can do it too. But how do you even test an idea that crazy?
Right. Well, it turns out there was already some experimental evidence to support this. Back in 1927, two American physicists, Clinton Davison and Lester Germer, were studying the scattering of electrons from a nickel crystal. And they noticed that these electrons were diffracting, which is something that we normally associate with waves. It's like these electrons were acting like water waves, passing through a narrow opening and creating this pattern of interference.
So this experiment was like the first concrete evidence that electrons, these tiny particles, could also act like waves.
Yeah.
That's amazing. It's almost like the universe is showing us this hidden duality, blurring the line between waves and particles.
Yeah, and this really set the stage for Schrödinger's groundbreaking work. He built on de Broglie's ideas and developed this mathematical equation that could describe the wave-like behavior of electrons and other particles.
Ah, yes. The famous Schrödinger equation. Now things are getting really interesting. Tell me about this equation. How did it revolutionize our understanding of the atom? What did it actually do?
Well, the Schrödinger equation, it's this really powerful mathematical tool that describes the behavior of matter waves.
Yep.
It governs how these waves, associated with particles like electrons, propagate and interact with their surroundings.
Okay.
It's kind of like the equations of motion in classical physics that describe how objects move.
So it's a way to predict how these matter waves will behave.
Right.
Just like we can predict the trajectory of, I don't know, like a ball being thrown using classical physics.
Exactly. But there's a really crucial difference.
Okay.
In classical physics, we can predict the exact position and momentum of an object at any given time. But in the quantum world, things are a bit more fuzzy.
Fuzzy. What do you mean by fuzzy?
So Schrödinger's equation, it doesn't tell us exactly where an electron is.
Okay.
Instead, it gives us this wave function represented by the Greek letter psi, which describes the probability of finding the electron at a particular point in space. So imagine it like this. Instead of the solid ball representing the electron, we have this cloud of probability, where the density of the cloud corresponds to the likelihood of finding the electron in that region.
So instead of knowing for sure where the electron is, we have like a map of where it's most likely to be.
Right.
That's a pretty big shift from the certainty of classical physics.
It is, and this probabilistic nature of quantum mechanics, it was a radical departure from the deterministic worldview of classical physics. And it's one of the things that makes quantum mechanics so mind-boggling.
I can definitely see how that would be unsettling for some physicists, especially those used to the neat and tidy world of classical physics, you know?
Right.
So Schrödinger's equation, it gave us this powerful tool to describe the behavior of matter waves, but it also introduced this element of uncertainty, this fuzziness that really challenges our understanding of reality. You know, that's a pretty big deal.
It is. And this tension between the power of Schrödinger's equation and these implications of its probabilistic interpretation, it became a recurring theme in Schrödinger's life and work.
I bet. But before we get into all that and into Schrödinger's famous cat, I think it would be helpful to take a closer look at this wave function.
Okay.
I mean, it seems to be at the heart of this quantum revolution.
It really is. The wave function is absolutely central to quantum mechanics. And understanding it is key to grasping the strange and often counterintuitive nature of the quantum world.
All right, so let's unpack it a little bit more.
Let's do it.
I'm ready to dive deeper into the world of the wave function and see where it takes us.
Okay. So yeah, the wave function, it's not just some abstract mathematical thing. It's a tool, you know? It lets us make predictions about how quantum systems will behave. Think of it like a map, but not a map of a location, a map of possibilities.
Map of possibilities.
Yeah.
So instead of telling us exactly where an electron is, it tells us where it might be.
Yeah, exactly. It gives us this range of potential outcomes. Okay.
Each with its own probability.
Okay.
So for example, you know, when we talk about an electron orbiting an atom, we can't pinpoint its exact path like we can with a planet around the sun.
Right.
You know.
Yeah, that's kind of hard to imagine. I mean, how do we even picture that? An electron not having a fixed orbit.
Well, instead of picturing this tiny little ball whizzing around a nucleus,
Right.
imagine a cloud surrounding the nucleus.
Okay.
And the denser the cloud is in a specific area, the higher the probability of finding the electron there.
Got it.
And these clouds, we call them orbitals, and they basically describe the regions where the electron is most likely to be found. And just like clouds, these orbitals come in different shapes and sizes, which influences how atoms bond and form molecules. Okay, so the orbitals are like these probability maps for electrons, and these probability maps are dictated by the wave function. It's starting to make sense. But I gotta say, it's still a bit strange to think about. Like, this probability thing, it's not like anything we experience in our everyday lives.
You're right, it's not. And this whole idea that the fundamental building blocks of matter behave in such a probabilistic way, it was really unsettling to a lot of physicists, including Schrödinger himself.
Yeah.
You know, he had this deep appreciation for the elegance and the determinism of classical physics, where everything seemed predictable and, you know, well-defined.
Right.
So he was really looking for a way to reconcile this new quantum reality with his classical intuition.
I mean, yeah, that makes sense. It must have been like trying to fit a square peg in a round hole, you know?
Right.
So how did Schrödinger grapple with this tension between the classical and quantum worlds?
Well, one of the most famous ways he explored this tension was through a thought experiment that has become really iconic in quantum mechanics. Schrödinger's cat.
Ah, yes. Schrödinger's cat. I've heard of this, of course, but I'd love to hear you explain it.
Okay, so imagine this. You have a cat, and it's inside a sealed box.
Okay.
And inside this box, along with the cat, there's this device. And it contains a single radioactive atom. Now, there's a 50-50 chance that this atom will decay within an hour.
Okay.
And if it decays, it triggers a mechanism that releases a deadly poison, which would kill the cat. But if the atom doesn't decay, the cat's fine.
Okay, a little morbid, but I'm following so far.
All right, now here's where the quantum strangeness comes in.
Okay.
According to quantum mechanics, until we open that box and observe the cat, that radioactive atom exists in a superposition of states.
Okay.
It's both decayed and not decayed at the same time.
Wait, hold on. You're saying that the atom is in two states simultaneously. How is that even possible?
Well, it's one of the fundamental principles of quantum mechanics. Superposition.
Okay.
It says that until a measurement is made, a quantum system can exist in multiple states at the same time.
Okay, so the atom is in this weird limbo state.
Mhm.
But how does this relate to the cat?
Well, because the cat's fate is directly tied to the state of the atom.
Right.
The cat also inherits the superposition. So until we open the box, the cat is, in a sense, both alive and dead at the same time.
Whoa. Okay, that's where my brain starts to melt a little bit.
Mhm.
You're saying the cat is both alive and dead until we look inside. That seems impossible.
And that's exactly the paradox that Schrödinger was trying to point out.
Okay.
You know, he was using this absurdity of a cat being both alive and dead to point out the problem of applying quantum superposition to large everyday objects, like a cat.
So he was basically saying, hold on, this quantum stuff, it's great for tiny particles, but when we try to apply it to everyday objects, it just leads to these crazy conclusions.
Exactly. Schrödinger's cat, it was a provocation, It was a way to force physicists to really confront the implications of quantum mechanics and wrestle with this question of measurement, Like, what does it mean to measure something, and what is the role of the observer in shaping reality?
Yeah. And it's a question that still haunts physicists today, right?
Yeah.
I mean, the act of observing a quantum system seems to actually influence its behavior. It's like our consciousness is somehow entangled with the fabric of reality.
It's a really deep philosophical question, and there's no easy answers,
Yeah.
But even if the cat paradox doesn't have, like, a definitive solution, it's led to some really fascinating ideas about how we reconcile the quantum world with our everyday experience.
Okay, I definitely want to hear about some of those ideas. How do we bridge this gap
Mhm.
between the strangeness of quantum mechanics and the seemingly predictable world that we live in?
Well, one of the most compelling ideas is this concept called decoherence. And it basically suggests that the reason we don't see macroscopic objects like cats in these superpositions is because they're constantly interacting with their environment.
Okay, so the environment plays a role here.
Right.
But how does that work?
Well, think about it this way. The cat inside the box isn't really isolated.
Right.
It's, interacting with air molecules, photons of light, even the walls of the box itself. And all these interactions, they act like these tiny little measurements, constantly nudging the system towards a definite state.
Okay.
So even though the cat theoretically could be in a superposition of alive and dead, these environmental interactions are essentially collapsing the wave function. And that leads to a single outcome.
So it's like the environment is constantly observing the cat, preventing it from existing in this weird, both alive and dead state.
Yeah, it's kind of like that. It's almost as if the act of observation isn't this special thing that we do consciously, but it's this fundamental process that's happening all the time, everywhere.
That's a really interesting way to think about it. So decoherence helps explain why we don't see quantum weirdness in our everyday lives. It kind of bridges the gap between the counterintuitive world of quantum mechanics and the familiar world of classical physics.
Yeah, exactly.
That's fascinating. It makes the strangeness of the quantum world a little more, I don't know, palatable,
Yeah.
Knowing that there are these mechanisms in place to prevent it from bleeding into our everyday experience.
Mm-hmm.
But even with decoherence, I mean, there's still so many mysteries surrounding quantum mechanics, like this idea of entanglement.
Oh, yeah.
It just seems so bizarre.
Yeah, entanglement, it's definitely one of the spookiest aspects of quantum mechanics. And, Schrödinger himself actually coined the term
Wow.
to describe this strange phenomenon where two particles become linked and their fates are intertwined even if they're separated by, vast distances.
Okay, that already sounds pretty weird. But why did Einstein call it spooky action at a distance?
So imagine you have these two entangled particles, we'll call them A and B,
Okay.
and you separate them, You send particle A to one side of the universe and particle B to the other side. Now you measure a property of particle A. Let's say its spin.
Okay.
The instant you make that measurement, you instantly know the spin of particle B, even though it's, billions of light years away.
Wait a minute. So information is being transmitted between these particles faster than the speed of light. That seems impossible.
It does, right. And that's exactly why Einstein found this so unsettling. It seemed to violate his theory of special relativity, which says nothing can travel faster than light.
Right.
He really believed that there had to be some hidden variable, some unknown factor that we weren't accounting for that would explain this seemingly instantaneous correlation between the two particles.
So it's like there's this invisible thread connecting these particles, allowing them to communicate instantly across vast distances. It really does sound spooky.
It does. And it's a mystery that continues to fascinate physicists today. We still don't fully understand the mechanism behind it, but we know it's real, and it has these profound implications for how we understand the universe.
And it's not just theoretical, right? I mean, entanglement is actually being harnessed for practical applications too.
Oh, absolutely. One of the most exciting areas is quantum computing.
Okay.
Where by exploiting these properties of entangled particles, we can build computers that are way more powerful than anything we have today. Imagine computers that could, crack the toughest encryption codes or design life-saving drugs or simulate complex systems with incredible accuracy.
It's amazing to think that this spooky action at a distance, this thing that Einstein had a problem with, could end up revolutionizing the world.
It really is.
So Schrödinger, the guy who almost became a linoleum salesman, ends up laying the groundwork for technologies that could totally reshape our future.
It really speaks to his genius and to the enduring power of scientific curiosity. His willingness to wrestle with those paradoxes and uncertainties of quantum mechanics. It opened up a whole world of possibilities. And his story doesn't end with quantum mechanics either.
Oh. There's more. I'm definitely ready to hear about Schrödinger's other adventures in science. What happened next?
Well, after his groundbreaking work on quantum mechanics, he turned his attention to a whole new frontier, the mysteries of life itself.
Interesting. So he went from the quantum world to the realm of biology.
He did.
It sounds like he had his hands in all sorts of things.
He did.
So we've talked about his life, his early influences, his amazing work on quantum mechanics, his struggles with how to interpret his own discoveries. And now you're telling me he went into biology too.
Yep.
What a journey. But, we've covered a lot of ground. Where do we go from here?
Well, let's talk about what is life. It's a fascinating book that really reveals his unique perspective on the nature of living organisms and how they relate to the laws of physics. It's like this bridge between the world of atoms and the world of cells, highlighting how interconnected everything is.
That sounds like a perfect way to transition into the next part of our deep dive. Let's explore Schrödinger's foray into biology and see how his ideas continue to shape our understanding of life itself.
So what is life? It's really a remarkable book.
Yeah.
It was published back in 1944.
Okay.
And it was based on these lectures that Schrödinger gave in Dublin. And what's really striking about it is how he approaches this whole question of life from a physicist's perspective,
Yeah.
He's bringing these tools of physics to bear on a topic that you wouldn't think is related.
That's what I love about Schrödinger.
Yeah.
He wasn't afraid to cross these disciplinary boundaries.
Right.
Like apply his knowledge to new areas.
Yeah.
So what were some of the big things he had to say about life?
Yeah. Well, one of the central themes of the book is this idea that living organisms, they have to have some mechanism for storing and transmitting genetic information. And keep in mind, this was before we even knew the structure of DNA.
So he was basically predicting the existence of a genetic code. That's pretty impressive.
It really is. He reasoned that life's ability to maintain order and complexity over generations, it required some kind of stable blueprint. And he even speculated that this genetic material might be a molecule with what he called an aperiodic crystal structure, which kind of foreshadowed the double helix structure of DNA.
Wow. So Schrödinger was like way ahead of his time, but he didn't just focus on the molecular side of things, did he?
No, not at all. He also explored how living systems manage to maintain order and complexity in a universe that's governed by the second law of thermodynamics.
Right. Well,
which basically states that entropy or disorder always increases.
yeah, that's a great point. It seems like life is constantly fighting against this tendency towards disorder.
Exactly.
How did Schrödinger try to make sense of that?
Well, he proposed that living organisms maintain order by constantly taking in negative entropy,
Okay.
or, order from their environment.
Okay.
Think of it this way, plants use sunlight to create these complex molecules from simpler ones.
Hmm.
Animals eat plants or other animals to fuel their metabolism and growth.
So it's like life is this constant struggle against entropy, a battle that's fought by extracting order from the environment.
Yeah, that's a great way to put it.
I never thought about it like that before.
It's a really profound insight, and it still shapes how we understand living systems today.
Yeah.
Schrödinger also, went on to delve into the nature of consciousness,
Okay.
suggesting that it might even be a fundamental aspect of reality, not just a product of our brains.
And that's a big idea. I mean,
Yeah.
we were just talking about how the act of observation seems to play a role in quantum mechanics.
Right.
Is he suggesting there's a deeper connection there between consciousness and the nature of reality itself?
It's definitely a question that he struggled with throughout his life, and
Yeah.
it's one that continues to be debated, by physicists and philosophers. What is life? It's really a testament to his curiosity, his willingness to explore the big questions, even if they don't have clear answers.
It's inspiring, really. I mean, here's this physicist who made these groundbreaking contributions to quantum mechanics, and then he shifts his focus to the mysteries of life,
Yeah.
bringing this totally fresh perspective and asking these profound questions
Right.
that still resonate today.
Exactly. His impact goes way beyond his own discoveries, His work has inspired countless scientists in
Yeah.
all sorts of fields: physics, chemistry, biology, computer science.
Wow.
He showed us that science isn't just about finding the answers. It's also about asking the right questions, even if they lead to, uncharted territory.
So, as we're wrapping up our deep dive into the life and work of Erwin Schrödinger, what are some of the key takeaways? What should we remember about this guy?
I think the biggest thing is that Schrödinger was more than just a brilliant physicist.
Right.
He was this polymath, a philosopher, a visionary, who really wasn't afraid to challenge how we think about things.
Yeah.
His equation, it's still a cornerstone of quantum mechanics, but his legacy is so much bigger than that.
Mm.
He taught us that the universe is full of surprises and that the quest for knowledge shouldn't have boundaries.
He was a reminder that science is driven by our curiosity,
Yeah.
by this desire to understand the world around us, from the smallest particles to these big questions about life itself.
Yeah.
And sometimes the biggest discoveries come from those who are brave enough to look beyond their own fields.
Absolutely. Schrödinger really showed us that the pursuit of knowledge should be this interconnected endeavor, and that the greatest breakthroughs often happen at the intersections of different fields. He was a pioneer in quantum mechanics, a visionary in biology, and just a testament to the power of human curiosity and intellectual exploration.
Well said. It's been a fantastic journey exploring the life and work of Erwin Schrödinger. I feel like I've learned so much about this complex and fascinating figure.
You too. It's been a pleasure diving into his world and sharing his story.
If our listeners are interested in exploring more, what would you recommend?
Well, if you're curious about how physics and biology intersect, What is Life is definitely worth reading.
Okay.
And for anyone who wants to go deeper into entanglement, check out the work of Anton Zeilinger. He's a real pioneer in quantum optics who's really pushing the limits of how we understand this bizarre and fascinating phenomenon.
That's great advice. And thank you for joining me on this deep dive. It's been really enlightening.
The pleasure was all mine.
And to our listener, we hope you enjoyed this journey into the world of Erwin Schrödinger. Until next time, keep those minds curious and stay tuned for more deep dives into the world of knowledge and discovery.